Much, and thank you very much for giving me the opportunity to speak to you today. So today I wanted to talk about something which I think could have quite significant implications for the wider astronomy field, and could impact things, for example, trying to estimate the mass and spin distribution of black holes given our gravitational wave observations. And I think this is going to become quite a significant problem now that we're starting to observe more extreme gravitational wave signals in sort of extreme regions of the parameter space. So what I'm going to do is I'm going to break down this title into a series of keywords, and we're going to go through this title one by one, and hopefully by the end of it, we'll all understand what this title means, and I can show you some nice new results. And if you're interested, you can read this paper here, which I'm going to be summarizing today, and I'm here until Friday, so you can grab me at any time and talk to me about this if you're interested. So firstly, what are gravitational waves? So firstly, I'm going to take a step back and ask the more fundamental question of what is gravity. So as we know, when you have two massive objects of masses m1 and m2, they're going to experience an equal and opposite force. And this force, this gravitational force, is going to be proportional to the product of the two masses and inversely proportional to how far away they are. So you're going to experience a very large gravitational force when you have very large, massive objects at a very close separation. And you're going to experience very weak gravitational force when you have small objects or very less massive objects very far apart from one another. Now, this theory of gravity works remarkably well when you're in sort of like the weak gravity regime. And it can, for example, predict the orbit of the Earth around the sun to very high accuracy and the orbit of the moon around the Earth. But it does have some limitations, mainly when you're in sort of like the strong gravity limit. And for example, it can't predict the orbit of Mercury around the sun. So this is where we moved on to general relativity, and this was Einstein's theory of gravity. So for this case, Einstein said that we have to completely rethink not only gravity, but space itself. And we should actually think of space as this fabric throughout space and time. And massive objects cause indentations in this fabric of space and time. So what you can see in this graphic here is this sort of fabric, this black fabric with the green lines through it. And you can see that when you have a massive object, for example, the sun, it causes an indentation in this fabric of space and time. And every massive object will cause an indentation in this fabric. So you can see here the Earth on the right-hand side here causes a much smaller indentation. But what Einstein said was that gravity should be thought about in this sort of form. And in sort of like a very hand-wavy way, you can think about gravity as sort of like the Earth falling into the potential well caused by the sun in this abstract sort of notation. And there's a very nice quotation here by John Wheeler, which basically says, matter tells space-time how to curve, and space-time tells matter how to move. And Einstein's theory of gravity can be summarized by this equation up here. I'm not going to go into details about it, but I added it just because I think it looks really pretty, and I absolutely love this equation. So if you consider a completely flat space, so a completely flat fabric, and you consider a very small perturbation on top of that fabric, you can basically show by solving Einstein's equations that this small perturbation will obey the wave equation. Okay, so there is a solution that has this wave-like structure that will travel at the speed of light. And this was noted as gravitational waves. So this is very important because it differs a lot from Newtonian theory of gravity, where for the Newtonian theory, if you were to remove the sun, for example, there'd be an instantaneous lack of force there. Whereas for the Einstein theory of gravity says that nothing can travel faster than the speed of light. So yeah, you're sort of limited to the speed of light there, and the gravitational waves travel at the speed of light. So what you can do is you can actually show by solving Einstein's equations that you can produce these gravitational waves by just accelerating matter. Okay, so there's a really nice graphic here, which hopefully it will work if I click here, which shows when you have two rotating objects in this fabric of space and time, you can produce these ripples on the surface of this fabric, and these ripples are these gravitational waves. So this is a really nice graphic, which was made by ex-PhD student here, Shanika. And this really shows the different types of gravitational waves that we're sort of sensitive to. So in the top left here, you have these short duration gravitational wave signals that are produced by compact binary coalescences. So for example, the collision of two binary black holes or the collision of two neutron stars. And you can also have sort of these longer duration gravitational wave signals. So this is, for example, a spinning neutron star with a mountain, for example, and you would get a continuous gravitational wave here. So this is sort of like a sine wave. You can also get gravitational waves through supernova. They have a very different structure compared to the previous two. And you can also get sort of like a stochastic gravitational wave background, which is a sum of gravitational wave sources for all of the different types, essentially. But in this talk, I'm going to focus on the compact binary coalescences, okay? And I'm going to specifically focus on the collision of two binary black holes and the gravitational wave emission caused by the collision of two binary black holes. So for this case, we have an object of mass m1 and m2, and they both have some sort of spin, s1 and s2. Okay, and I'm sort of going to talk about this in a bit more detail throughout this talk, but two things I want to sort of focus on is this sort of parallel spin. So this is the effective parallel spin. It's a mass-weighted product, essentially, but it tells you how much spin in the binary is aligned with the orbital angular momentum. And you also have the perpendicular spin, again, a mass-weighted combination, which tells you how much spin is perpendicular to the orbital angular momentum, or within the plane of the binary. So I will be referring to those two throughout this talk. Okay, so now we're familiar with gravitational waves. Let's now talk about gravitational wave Bayesian inference. So firstly, what is Bayesian inference? Well, Bayesian inference is the technique to be able to infer the properties of a model given some data. Okay, so if, for example, we have some data here which is just randomly generated with some random y error, and we're interested in fitting a straight line to this curve. So our model is just going to be y is mx plus c, where we have some unknown gradient m and some unknown intercept c. We can essentially use Bayesian inference to be able to predict or to be able to infer what the gradient and intercept is given this data. Okay? So what we can do is we can use different techniques I'll come on to in a moment to be able to infer these properties, and you can get a probability distribution for the intercept as well as a gradient here. Now, of course, we could do, for example, least squares regression and get a single line or a single point here to get the best fitting gradient and y-intercept. But through Bayesian inference, we can also get some sort of uncertainty associated with it. So we can see here that the most likely gradient and intercept is probably going to be somewhere around here. So a gradient of maybe minus 1.05 and y-intercept 4.6 maybe. But what's really interesting about this is you can also see there is some sort of correlation between these two parameters. And you can see that if the gradient was in fact -1, that would correspond to an intercept of around 4.2. So through Bayesian inference, you can see these correlations between these parameters here. And you can actually do exactly the same thing for a time series. So here you have a time series. This is actually some gravitational wave data that was observed by the LIGO-Livingston detector, I think, for the first gravitational wave observation. And we can do exactly the same thing. We can take a model for the gravitational waves, and we can use Bayesian inference to be able to find the best fitting parameters to understand or to sort of model this data. So we can take that model, and we can try and infer the parameters lambda given this gravitational wave data. And again, you can get a very similar thing to the previous slide, and you can infer, for example, the masses of the two objects that collided to produce that gravitational wave. Okay, so here you can see, I believe this is for GW150914, you can see that this was most likely produced by a binary black hole merger of masses around 34 times the mass of our sun and around 31 times the mass of our sun. And you can just do this through Bayesian inference. Now, Bayesian inference is completely understood through this single equation here, and this is Bayes' theorem. So Bayes' theorem tells you how to calculate the probability of your model parameters lambda given your data D and your model M, okay? And this is what's known as a posterior distribution. Okay, so in order to calculate the posterior distribution, we need to be able to calculate or understand the prior. So the prior is our prior knowledge of what we think those binary parameters lambda are given our model. So we can, for example, assume completely agnostic priors and say for the case of binary black holes, we can say that all binary black hole masses are equally likely. We can say, for example, if you have a binary of masses 101, that's as equally likely to form in nature as a binary black hole with masses 10 and 10, for example. Or you can assume sort of like an astrophysical distribution And you can say it's much more likely to form a binary black hole with masses 30 and 30 than 1,002, for instance. It's completely up to you how you define your prior distribution, but it's very important to be able to quantify and say what your prior distribution is prior, because it is going to be it is going to make an impact on your posterior distribution there. You also have your evidence term. So this is your denominator in this equation. And this is, for all intents and purposes, essentially a normalization constant. It's the integral of the likelihood times prior overall parameter space. And as I alluded to, we also have the likelihood term here. So the likelihood tells you what is the probability of the data given your parameters lambda and your model M. Okay? And for gravitational wave data analysis, we actually can write down the likelihood. It's very well known. For other fields, this isn't the case, and you have to do, for example, likelihood-free Bayesian inference. But for gravitational wave astronomy, we know the likelihood. And the likelihood takes this very simplified form. We have that our likelihood, our probability of the data given our binary parameters lambda and our model M is essentially the exponential of this term here. I'm not going to go into details as to what this term is, but just to highlight some of the key features, we have D, which is our gravitational wave strain data. That's our time series that I showed you a moment ago. And this is simply composed of signal plus noise. Okay, so some unknown signal that's masked by noise in this gravitational wave data that we're trying to infer the properties of. And we also have our gravitational wave model M. Okay, so we need to be able to have a model that takes in a set of binary parameters lambda, and it will produce a gravitational wave signal. Okay, we need to be able to produce a gravitational wave signal for every set of binary parameters lambda. Now, it is completely possible that we could, for instance, have a very accurate model. We could numerically solve Einstein's equations for a given set of binary parameters lambda and get the exact gravitational wave signal for every set of binary parameters lambda to subtract from the data. But in reality, that's not going to be the case, because actually solving Einstein's equations of gravity for a binary black hole system is very expensive. So we have to produce these models to actually give us the gravitational wave that we think would be produced by two binary black holes, or two black holes of parameters lambda. So if we just take a random set of binary parameters lambda, and we generate a gravitational wave signal according to our model, we can essentially compare it to the data here. So you can see in gray, this is that gravitational wave data D, which contains some signal and noise. And in white here is the model evaluated at some random set of parameters lambda. And you can see that if I flick back and forth, that does not describe the data at all. We can see there's some additional oscillations in the signal, which is not in the gravitational wave data. So if we were to subtract the two, we're going to get some residual term, and we're not going to get a high likelihood as a result, because the likelihood is simply the difference between D and M here. So you can see that here we're actually going to have quite a low likelihood. I could choose a completely different set of binary parameters lambda and do exactly the same thing. Produce a different gravitational wave signal according to our binary model M, and again subtract the two, and we're going to again see that this is not a good fit to the data. We have quite a low likelihood here, because again it's predicting some additional oscillations that's not in the data. So you can see here, for instance, we get an additional oscillation here, which is not in the data there. Okay, so it's going to have quite a low likelihood when we subtract the two. However, if we find the perfect set of binary parameters lambda, and we generate the model associated with that, we can now see that we get all of the oscillations. We perfectly describe the oscillations there, and as a result, we're going to get a high likelihood. Okay. Now, in reality, we don't do this. We don't just randomly generate binary parameters lambda, evaluate our model, and compare it to the data. What we do is we do stochastic sampling, which I'll get onto in a moment. But essentially what we do is we change these parameters one by one and generate these gravitational wave signals and compare to the data. So in blue here, you can see your gravitational wave data D. And what you can see in orange is our model evaluated a set of parameters lambda. And this is a really nice graphic produced by Cardiff University, which shows exactly that. So what I'm going to do is I'm going to change the binary parameters one by one, and I'm going to try and find the parameters that perfectly describe that signal. So firstly, what I'm doing is I'm changing the total mass here. And what that is essentially doing is changing the wavelength of my gravitational wave signal until I get a point, until I get a mass which actually describes the wavelength of the signal. So you can see here that's around 65 m. And then what I'm going to do is I'm going to change, oh, sorry, let me play again. There we go. And then once I've got the wavelength right, or the frequency, I'm then going to change the amplitude of my gravitational wave by essentially changing the distance. So you can see now I'm going to change the distance. I'm going to reduce it to change the amplitude of my gravitational wave signal until, again, it has roughly the right amplitude. And then I'm going to apply what's known as a detector sensitivity, to how sensitive our detectors are to different regions of the sky. And then we get a signal or a model that really nicely describes the data there. So just to see again, we change the total mass to get the frequency and wavelength right, and then we change the distance to get the amplitude right, and then we change essentially the sky location to try and get the low frequency bit right down here, until we get to a point where our model, our orange curve, looks like the blue. Now, as I alluded to, we don't do this in practice. What we do is we use stochastic sampling. So what does this mean? Well, what we do, there are different techniques or different stochastic sampling methods, but I'm just going to talk about nested sampling here because it's relevant for the rest of the talk. But for nested sampling, what you essentially do is you take n points, these live points, let's say 100 points, and we randomly throw them in our prior volume, okay? So here we have a square, this is our prior parameter space, and we just randomly throw these points in this parameter space. And what we do is we calculate the likelihood for every single point in that parameter space, okay? What we then do is find the point that has the lowest likelihood, and we evolve it to try and find a point of higher likelihood. So we take this point, we make it a dead point, is a technical term, but we essentially remove it, and we move it to a higher point of higher likelihood through different techniques. And we just keep doing this one by one until these points converge to the highest likelihood region. Okay, so every single point, we're just removing one, moving it to a higher likelihood point, and eventually these points will converge to the highest likelihood point. Okay, so you can see here that we started from a very wide parameter space, and now we've moved to a very tight region of high probability, which is very tightly constrained around 0 and 0, for instance. So this is what's known as nested sampling. There are different ways of doing the stochastic sampling, but nested sampling is one of the most popular in the gravitational field at the moment, and is going to be relevant for the rest of this talk. Okay, so now that we understand gravitational wave Bayesian inference, what do I mean by incorporating models into gravitational wave Bayesian inference? Okay, so as I mentioned, our likelihood is completely dependent on our gravitational wave model M. Okay, everything is dependent on this model, and we need to be able to generate a gravitational wave given some set of binary parameters lambda. And we need to do this relatively efficiently because it is very expensive to be able to walk around this 15-dimensional parameter space that's associated with two merging binary black holes, and we need to be able to produce the likelihood for every single point of binary parameters lambda. So we need to be able to produce these models, and thankfully, there is now an ensemble of different models available to us that we can use. I won't go into details as to what each of these models are and the different assumptions, but what I'd like to pay attention to is that each of these models, for each of these three gravitational waves here, they were all produced from exactly the same set of binary parameters lambda. And you can see that for these three cases, the gravitational waves look completely different from one another, okay? So if we had some gravitational wave data D, and we were to subtract this waveform from the data, we would get a very different likelihood from one where we were to subtract this waveform from the data. Okay? So everything is dependent on our gravitational wave model, and in some cases, the models can differ quite significantly, which means our likelihood is going to differ very significantly as well. So how do we get around this? Oh, well, okay. So this is a really nice plot which shows the impact of our different gravitational wave models. So as I mentioned, you can see these different models can look very different visually for different sets of parameters lambda. And if I were to actually perform Bayesian inference and get some sort of distribution for the spins now, so this is a perpendicular spin and a parallel spin, as I mentioned earlier, if I were to do that and analyze some real gravitation or some simulated gravitational wave data for a given model M, here we can see that the probability distribution peaks at the injected values. So the injected values here are shown by the vertical and horizontal lines, and this is the 90% contour here. So you can see that for this given gravitational wave model, we perfectly capture the injected values, okay? However, for a completely different model, you can now see that the 90% contour does not encapsulate the true value at all. If we were to, if this was actually real data, we would incorrectly infer that this was actually had very low in-plane spin with perpendicular spin or with parallel spin around minus 0.5. And that's actually incorrect given our true source parameters there. Whereas for this gravitational wave model, we'd accurately understand that the amount of perpendicular spin was actually around 0.55 for this simulated data at least. So what you can see here is that if we were to just trust this model, we would get completely the wrong binary parameters. And if this were to happen over and over again, and we were to see lots of these gravitational wave signals, we might incorrectly infer, for example, that black hole spins are very small within the plane of the binary. Yes?
Saying, okay, gives different results than the other, but now you're saying this one is the wrong one. So which of these gravitational wave models is actually wrong or not?
So for this case, this was a simulated gravitational wave signal.
Yeah, exactly the same thing. Signal that also assumes the same kind of model for the simulation of the data.
So this was actually numerically solving Einstein's equations. So I had sort of like a true, assuming numerical relativity was correct, then I have a true solution. And then I were to analyze them with the different models. Yeah. So for this case, this model does not describe general relativity correctly. And the problem is that we're now starting to see this in our real gravitational wave observations. So this is one gravitational wave observation that was observed in 03. This was GW200129. And what you can see here are the resulting posterior distributions from two very different models. Okay, you can see that for one model, our 90% contour says that the mass ratio here, which is defined as the primary or the secondary mass divided by the primary mass, so always less than 1, you can see that one model says that it's approximately equal mass ratio binary, with primary spin, A1, around 0.3-ish, but a relatively wide posterior there. For a completely different model, we're actually inferring that it's a 2-to-1 mass ratio binary with very highly spinning components. Okay, so we're starting to see these differences already. This isn't just in simulations, we're starting to still see this in real gravitational wave signals as well. So if we were to just trust this orange model, we would infer that the primary object was rapidly spinning. If we were just to trust this white model, we would say it's very unlikely to have high spins. And this has significant implications if we were to look at the overall spin distribution of black holes. For instance, if we were to just use the white model for all of the gravitational wave observations we've seen so far, we might infer the spins are much lower than if we were to infer this or use this orange model, for instance. So this is why I think this is going to start becoming a real problem. For regions of the parameter space that are not massively exciting, so for example, equal mass ratios and low spin, these models agree very well with one another, and all of the contours will overlap. But as we start to get to these sort of extreme regions of the parameter space, which are sort of like these high mass ratios and high spins, this is where our models start to disagree, okay? And we will start to see these differences between these posterior distributions. And as our detectors become more sensitive, we're going to also see much louder gravitational wave signals, which again will amplify these differences, okay? So this is why I think this is going to become quite a significant problem as our detectors are becoming more and more sensitive, and we're starting to increase the number of gravitational wave signals that we're starting to see. Yes? So we don't know what the true binary parameters are. But there are cases, for example, in this paper that we wrote for GW2129, we did a very similar thing. We took the known numerical relativity solutions, and we compared this model to numerical relativity, the orange, compared to the white, and showed that the orange model is more likely to be accurate. But the issue is performing numerical relativity and analyzing or solving Einstein's equations is actually very expensive. So for instance, when I used to perform numerical relativity, it would take around 6 months to get a single numerical relativity simulation. So in reality, we can't really do this. And that's why in the whole field, there's only around 3,000 numerical relativity waveforms available currently, publicly available currently at least. So although ideally you would do something like this, in reality, it's quite challenging. So yeah, well, this is a bit technical, so we can follow up maybe after. But yeah, there were some data quality concerns. Here we're analyzing data that had removed those data quality issues. There have now been numerous papers to look into different ways of subtracting the data. Some ways say that it's very highly processing with more significance than what we found and things like this. But we can follow up later for this specific event. But yeah, the key point is that we are starting to see these differences between our gravitational wave models for real gravitational wave signals. So one way that can be done to sort of combine our different distributions as a function of our model M is to do what's known as Bayesian model averaging. So here what we do is we calculate the posterior distribution for every single set of model M that we wish to use. So in this case, that would be that orange curve, and that would be the white curve in the plot before, and would simply combine them according to this equation here. So we'd take those posterior distributions and we combine them according to some probability for the probability of the model given the data. So what we would do is for each model, we would calculate that posterior distribution independently and then combine them after the fact in post-processing, essentially. So the standard approach would be just to say that all models are equally likely. We don't know which one's more likely on average, so we just say they're all equally likely, and therefore we essentially equally combine the posterior distributions for every single model. The other technique is what's known as this evidence-informed approach. So that's coming back to what I mentioned earlier. You calculate these evidences, which is that denominator of that Bayes theorem, and you combine according to those different evidence terms. And the idea is that a model that has a larger evidence fits the data better and will therefore more likely describe your true gravitational wave signal. So it should be upweighted, essentially. So essentially, we average our posterior distributions according to different weights that are dictated by that evidence term. But one of the big issues is that that doesn't account for model accuracy. Okay? And this comes back to the fact that we do know how accurate our gravitational wave models are by comparing to solutions of general relativity. So what we can do, although it's expensive, we can numerically solve Einstein's equations for a given set of binary parameters lambda. So for example, here, this is a gravitational wave signal for a given set of binary parameters that was produced by Mike Boyle et al. So this is part of the SXS collaboration. But we are able to produce an exact solution of Einstein's equations of general relativity, assuming numerical relativity is correct, for a certain set of binary parameters lambda. And what we can do is we can then evaluate our models for exactly the same set of binary parameters lambda and look at how similar they are to that true signal, that true numerical relativity signal. So what you can see here in the white is our model evaluated at a certain set of binary parameters lambda, and in gray, you can't see it here, you can just about see it there, is the numerical relativity solution. Okay, and we can essentially compare the two and look at how similar they are to one another. So here for this model, you can see they're pretty much indistinguishable from one another. But for this model down here, you can start to see significant differences between what the model thinks the gravitational wave produced by a set of binary parameters lambda is and what numerical relativity says that the true gravitational wave signal is. And again, for this model here, you can again see that there is starting to be these significant differences between what the model predicts and what general relativity predicts. So we exactly know how accurate, or we can work out roughly how accurate our models are to general relativity by just solving Einstein's equations, producing these numerical relativity solutions, and then comparing our model to those solutions. And what we can do is we can quantify this by calculating what's known as a mismatch. I won't go into details, but the mismatch varies between 0 and 1, where a mismatch of 0 means that the two signals are indistinguishable from one another, they're completely identical, and a mismatch of 1 means that they're completely orthogonal. So just to put that into perspective here, for this model where the white looks just like the gray, we'd get a very small mismatch, around 10 to the minus 4. And for this case here, where the white doesn't look like the numerical relativity simulation, we get a much larger mismatch of around 10 to the minus 2. So we can calculate these mismatches for the known set of numerical relativity simulations that have been produced. And like I said, there's around 3,000 of these currently that are publicly available, at least that we can compare our models to. So, like I said, we can evaluate this mismatch, this quantity of how similar these two models are, and we can do this across the parameter space. So this is that perpendicular spin and the mass ratio here. And you can see that essentially if I were to calculate this mismatch across the parameter space, we get very good accuracy for mass ratios around 1, so equal component mass binaries with low in-plane spins. So here we expect all our models to look just like solutions to general relativity, okay? However, as we start to get to these more extreme regions of the parameter space, so as we start to get to very high in-plane spins, we start to see these big differences between our models and our true solutions of general relativity. And again, as we start to get to very high mass ratios, we see the same sort of thing. So in essence, our models are becoming more and more unreliable as we get to these more exciting regions of the parameter space. Really high mass ratio binary black holes and really high in-plane spin binary black holes. But the key point is that we can calculate this mismatch across the parameter space. We are able to tell you which model is more accurate in different regions of the parameter space, but our techniques do not currently incorporate this information. So this is where I wanted to talk about how we can incorporate model accuracy into gravitational wave Bayesian inference, and how we can incorporate the fact that we know what the mismatch is. We know how accurate our models are to true solutions of general relativity, but how can we actually incorporate that? So the key point here comes down to this, that our likelihood is completely dependent on our model. But what I'm going to propose to you is, instead of just using a single model here, why don't we just randomly choose our model associated with the mismatch? So we have some probability distribution for our model mi given our set of binary parameters lambda, and we're always going to use, or we're going to upweight anyway, the model that is more accurate to general relativity. And we're going to use that model to evaluate the likelihood. This way, we know that we're going to always use the most accurate model to general relativity for that given region of the parameter space. Okay? So as we know, different models are more and less accurate in different regions of the parameter space, so this is going to account for that. We're going to always use the most accurate model in each region of each region of the parameter space, so we know we're always going to get the most accurate likelihood as a result. And through trial and error, we said we're going to assume this prior distribution here, which goes as mismatch to the power of -4. Okay? And the reason we did this is because we wanted to amplify the difference between a model that has mismatch 0.99 compared to a mismatch of 0.999, for instance. And this is one way to do that. So it's really to amplify those differences between the models. So what we propose doing is that for each set of binary parameters lambda, during your stochastic sampling, you basically evaluate the mismatch and use the model that is more accurate to general relativity. So just to put that into perspective, what we do is when we do our nested sampling here, and we calculate or we identify the point that has the lowest likelihood, we move it to a point of higher likelihood, what we do is we propose a point, we calculate the mismatch for each of our different models, and then what we do is we choose the model which has the best mismatch, or the smallest mismatch in this case, to evaluate the likelihood. And like I said, that means that we're always going to use the most accurate model to general relativity to be able to evaluate the likelihood and get the most accurate likelihood as a result, and hopefully get the most accurate posterior distribution as a result as well. So the hope is that it's going to be more accurate than Bayesian model averaging in general. Now, one bad thing is that actually calculating mismatches is very expensive. Okay? So for instance, for this case, if we were to run on 64 processes just to calculate a single mismatch between a model and general relativity, we're looking at around 186 seconds there. Okay, so that's to calculate a single mismatch. And when do I perform Bayesian inference? I'm evaluating the likelihood around 100 million times. So that would mean that I'm going to have to calculate these mismatches around 100 million times, which is completely unfeasible. So we can't calculate the mismatch analytically for every single point in the parameter space because it's too expensive. So what we actually do is we calculate this fit to the mismatch manifold. We calculate loads of mismatches around the parameter space, and we essentially fit those points here. So this is what's shown here. You can see these random points in the parameter space. This is parallel spin now, and mismatch on the y-axis. And you can see that there is some uncertainty associated with each measurement. That comes from the fact that we're going to average over the sky and all this sort of stuff. But the key point here is that we take those points in white. We will come back to the how to incorporate errors later, or we can discuss that later as well. But what we do is we just take these point estimates, these means, and then we just fit a model across the parameter space. And what that means is that we can evaluate the model, which is significantly less expensive, and we can evaluate the mismatch for each point in the parameter space very accurately. and significantly cheaper than it is to analytically produce these mismatches anyway. So you can see here that if I were to calculate or I were to evaluate the fit at each of these points, you can see that the line is a very good representation of that true or the mean mismatch between numerical relativity and the model. And what we found was that by fitting the mismatch manifold and generating this fit, all of the actual calculation of the mismatches reduces to around 10 to the minus 1 seconds, 10 to the minus 2 seconds, which means that it's a lot more feasible during a Bayesian inference analysis. So now we get onto the results. What does this actually mean? So in orange is this technique that I've just proposed to you, that what we're going to do is we're always going to use the most accurate model in each region of the parameter space to evaluate the likelihood. In white solid, this is that evidence-informed approach that I mentioned earlier. So we combine the results from different independent analyses produced by different models. We're going to combine them according to the evidence term. And we have the standard approach, which is essentially to give all of the models equal weight and just to combine at the end. And what we did is we analyzed a numerical relativity solution where we have that true or known set of binary parameters lambda. And that's what's shown here. So we have the primary mass and secondary mass, and the true values are shown by the vertical and horizontal lines. So what you can see here is that if we were just to look at the standard approach, so the dashed white line, we can see that it does capture the true value within the 90% contour, but it is much wider than the other contours. And if we were just to look at the evidence-informed approach, we only just encapsulate the true value at the 90% confidence region. However, our NR-informed approach, that's taking the most accurate model to numerical relativity at each point in the parameter space during the inference, you can see that we obtain a much tighter distribution for the primary mass and secondary mass while still encapsulating the true value there. Now, this doesn't look too bad for the primary mass and secondary mass, but as soon as I move to the spins, things become quite significant here. So you can see that if we were just to look at the evidence-informed approach, our contour does not capture the true value at all within the 90% confidence region. So here's our true value down here, and it is completely miscapturing the value. So it says, according to the evidence-informed approach, that the effective perpendicular spin, so how much spin there is within the plane of the binary, is around 0.25, and effective parallel spin of around 0.1. Which is completely different to what the injected value is, which is around 0 perpendicular spin and around, 0.4 perpendicular spin and around 0 parallel spin. So it doesn't capture it at all. Yes?
So I'm going to check another question. So how sensitive is the quality of these matches to the amount of noise that you put in the system? If you have much better, clearer signals, say from newer generations of new observation ones, will this become tighter, or does the residual thing apply? So if you go to the extreme case where you reduce noise basically to 0 and thus just in a direct matching, is the same still true that this contours, or is that without any noise?
Yeah, so in general, your width of your posteriors will scale with the SNR. So as the SNR gets much louder, as your gravitational wave signals get much louder, your contours will get much tighter. So this is actually 0 noise. So this is without any noise in the gravitational wave detectors. You will see some movement of these contours as a result of noise, but this is the perfect case where there is 0 noise in the detectors, and we're still miscapturing the true signals here. If we were to just look at the standard approach, which is to equally... Oh, yes, sorry, Eric. Mm. So this is a very interesting question and something that we've been thinking about for a little bit of time as well. And I think this comes down to the fact that during your Bayesian inference analysis, we're not going to evaluate our model at the perfect set of binary parameters, and that's not going to give the perfect mismatch. During our Bayesian inference analysis, we're actually going to use what's known as the effectual parameters, which is going to be something completely different, but given that's going to evaluate your model to look just like the signal. Okay? So in other words, although the mismatch at the true binary parameters between your model and your signal might be very low for a given model, if for a completely different set of binary parameters, so up here somewhere, it manipulates the model due to mismodeling to give a gravitational wave signal that looks just like the true signal, then it's going to get a high Bayesian evidence as a result. It's going to look just like the data. But according to the mismatch, at those set of binary parameters, lambda is actually not a true description of general relativity. Because of mismodeling, we can produce a gravitational wave signal through the model, which looks like the true signal, but at the wrong set of binary parameters. So that was our sort of understanding as to why you can get gravitational wave models that get a high evidence, but a poor mismatch. Because it is the fact that you can evaluate them at different set of effectual parameters that will get high Bayesian evidence and look like the signal, but actually a poor mismatch, because when you generate those numerical relativity simulations at those true set of binary parameters, you get a model that doesn't accurately describe general relativity. Yes? Yeah, so it is. So there are lots of different assumptions that go into how we can generate these models, and you can do them in, for example, the time domain. You can do them in the frequency domain, and for example, you can treat it as an effective one body, or you can just do sort of like a phenomenological fit across the parameter space. And these are all different ways in order to describe those gravitational wave signals. And in general, what you do is you generate your model according to your default assumptions, and then you compare it to numerical relativity and try and tune those binary or tune those parameters of your model to make it look like numerical relativity over the vast parameter space. Yeah. So yeah, you would tend to always validate it against a given set of numerical relativity simulations, but because there's so few, you do end up using the same ones for each of the models. But because there's so few and you're essentially interpolating between those two, you can get very different points between those, or very different models between those known numerical relativity simulations. Yes. Yep. So each. Oh. Yes. So it's essentially saying for each point in the parameter space during the sampling, how are you choosing the model? Are you choosing all of them, or are you just always choosing the one which has the best mismatch? So what we do is that for each point in the parameter space, that we choose the new likelihood as we sort of progress those nested sum or those live points to the point of high likelihood. What we do is we take that point that's been proposed and we evaluate the mismatch through the fit for every single model that we want to use. So for instance, for this analysis, a bit technical, but we use phenom XPHM, phenom TPHM, and NR surrogate. And SEOB. And what we did is we calculated those mismatches for each of those points, and then we assumed this prior probability goes to m to the -4, and then chose our model associated with that. So we didn't always use the model that was most accurate to numerical relativity. We did some sort of probability distribution associated with it, but we significantly upweighted the model that was more accurate to general relativity. Yeah, so that was a valid option. We just chose to use a probability distribution in the end. But you could 100% just always use a model that's more accurate to numerical relativity for sure. But we just decided just to use a probability distribution in the end, just so you could have some probability of using a model that was less accurate. So as you can see here, for the NR-informed approach, we actually are able to capture the true value at the 90% contour. We only just capture it, but we capture it nonetheless. And our technique is the only one to be able to capture that true value in the 90% contour. And we are able to also significantly reduce the uncertainty on the effective perpendicular spin as well compared to the other techniques. So then what we wanted to do was analyze a real gravitational wave signal and see how our technique could help from an astrophysical point of view to sort of constrain the binary parameters. So this is for GW 191109, one of the gravitational wave observations, I think, from 03. And again, what we do is we compare to the standard and evidence-informed approaches. And you can see that for the evidence-informed and standard approaches, we can't pull away from an equal mass ratio binary. At the 90% confidence region, there is some probability that it is an equal mass ratio binary. and there is some width associated with the total mass measurement. But what's really cool is that when you use our technique, you are able to pull away from that equal mass ratio boundary line. So we know that it is not an equal mass ratio binary, and we're able to significantly reduce the width on that total mass measurement as well, compared with, for example, the standard approach and just equally combining all of the models and all of the independent measurements. So what we hope is that by using this NR-informed approach and always upweighing the model that's more accurate to general relativity, we can actually help from an astrophysical point of view and be able to say that for this case at least, it was not from an equal mass ratio binary, which could have significant implications as we get to these more extreme mass ratio binaries as well, and these more extreme regions of the parameter space, where we start, or where we think we'll see these differences between the evidence-informed standard and NR-informed approaches as well. So just to summarize, gravitational wave Bayesian inference in general does not account for model accuracy, or the existing techniques don't account for model accuracy. But it is possible to incorporate model accuracy by using a technique like what we described. So it is to upweigh the model that's more accurate to numerical relativity in each point of the parameter space during our nested sampling analysis. And in general, the method that we propose is actually future-proof as more accurate models become available. So waveform modeling is always constantly improving as we're able to reduce the number of assumptions that go into these things. We're able to always produce more and more accurate models, and our technique will always be able to fold in the newer models as they become available. All we have to do is calculate these mismatches for each point in the parameter space, and then calculate an interpolant and fold them through our pipeline. So we can always account for more accurate models as they become available to us. So yeah, so that's the end. Thank you very much. And let me know if you have any questions. Thank you.
Question on Zoom. I don't know if you can actually read it because it becomes part of the question. Tom.
Okay. Sorry. With this method, if I were to evaluate the likelihood at some combination of parameter lambdas one at a time, and then I later evaluated the likelihood at the exact same combination of parameters, would I always get the same number each time? It sounds like the answer is no, because there is some randomness in which the model you select at each likelihood evaluation. So yes, so if I were to calculate the set of binary parameters lambda during our nested sampling analysis and evaluate the model, there is going to be some randomness associated with which model I were to choose according to that probability distribution. We are able to say that we always use the same model each point, but we chose to keep it somewhat random by assuming that probability distribution. That was just one of the assumptions that we used, but you could 100% just always use the more accurate model to remove that randomness associated with the likelihood evaluation.
When you run nested sampling, so you expect to get to higher and higher likelihood, but then you change your model, and when you do it randomly, and so you might get to a lower likelihood region than you were before. So how does your sampling actually handle that?
So yeah, so this is getting into a bit more technical detail of how nested sampling essentially works. But there is some probability. So you would always jump to the point that has higher likelihood in general. If it has lower likelihood, there'll be some probability that you jump there according to the Metropolis-Hastings algorithm. But in general, you always jump to the point that has higher likelihood in general.
Right. And that's exactly my question. So if you replace your model and now you get lower likelihood,
then you wouldn't accept that point. But then you would then propose another point and again evaluate the likelihood or the mismatch there, and then use a model that has more accurate and then get a higher likelihood as a result.
So yeah, but you might get discontinuity, right? Because you are using like two adjustment points with exactly like the comment in the Skype or whatever that are, that you get different values for a very close by parameters. So that might break the nested sampling algorithm, I suspect. Maybe it's because the waveforms are so close to each other, so essentially you're not encountering that issue, but...
So this is a very good question, and we should probably chat more offline so we can go back and forth. But yeah, we can chat afterwards.
I'm seeing, I saw your hand there. Let's see.
All right, thank you so very much.
Sorry, wait for the microphone.
Sorry.
All right. So thank you so very much for the wonderful talk. So, I mean, my question is then to the reference thing. So, namely, how much do we trust the numerical relativity simulations? For example, is it a homogeneous set of simulations or heterogeneous? Do they agree with each other? Do we have reasons to believe them? How can we improve and things like that?
So this is a good question. So there are numerous numerical relativity codes now that can numerically solve Einstein's equations. The hope is that they give the same solution, but it's actually quite difficult to compare them. And the reason for that is because they all, how they account for the initial conditions of the binary and how they can do that. And it's actually quite a difficult problem to be able to compare the numerical relativity solutions for the exact same set of binary parameters for the different codes. That being said, we hope that the solutions to numerical relativity are quite accurate. You can sort of do a convergence test to see how accurate they are for each set of codes, and then you can get some sort of mismatch threshold based on that. And there are several orders of magnitude more accurate than the models, for instance. So the hope is that the numerical relativity is accurate to general relativity, but there is no guarantee for that. And yeah, comparing the different codes is actually quite a challenge because of how they define those initial conditions. So it's a more complicated question, unfortunately.
But that's encouraging. Thank you.
Ethan, I think, Eric, sorry, I'm leaving you for last, going to younger people first. Apologies.
Thanks for the interesting talk. Do you notice any trends with like which models tend to have like the most like, which waveform is the best based off your work here?
So for the models we chose, which was Phenom X PHM, Phenom T PHM, and SEOBNR V5 PHM, we found that SEOBNR V5 PHM was the more accurate one according to the mismatches. And that's one that we generally used when we were performing these analyses. We could incorporate other models, but those were the three that we chose to incorporate into our analyses.
Yeah. Do you know like what fraction of samples you end up like calculating with each one? And is it close or does it just dominate?
We'll have to check the paper for sure, but I think SEOB pretty much dominated for the models, for the NR models that we chose anyway. There are different regions of the parameter space where different models will be upweighted, but for the models we chose, SEOB was the majority. I would have to check the paper, but I think it was around 80-90% of samples. But yeah, we can check after to get an exact number.
Thanks.
I see you have a run, but actually this time I will go to Eric. Sharon asked a couple of questions already, so Eric, please go ahead.
So Sharon asked during the talk about just using the best approximant, the best waveform model. And in your answer to Tegan, you suggested that one of them kind of ran away with it. If that's the case, that one model is just better than the others, an easy solution would be to just use that one for inference. Do you have a use case where you can kind of show that you have two models that each outperform each other significantly in different parts of parameter space where it's really helpful to combine them?
Yeah, so this is a very good point, and you can show in different regions of the parameter space, certain models are more accurate than others. So just to follow on from that, there is a point in parameter space where, so generally the NR surrogate is going to be the most accurate model over the parameter space. And it is an order of magnitude more accurate than the other models, according to accuracy to numerical relativity. But there are regions of the parameter space within the calibration region of the surrogate where it's actually less accurate than all of the other models. Okay, so you can actually pull up regions of the parameter space where the surrogate is less accurate than the other models. And the reason for that is because the surrogate does just use this interpolation between the known numerical relativity solutions. So in a very similar vein, there are regions of the parameter space where Phenom X PHM is more accurate than SEOBNR V5 PHM. So we argue that you shouldn't just always use one model because of that. You're going to get low likelihood in those regions for that given model, which is less accurate, and you should always sample over the model with that mismatch. So this is arguing why you shouldn't always just use a surrogate for that case as well.
Sure.
I was wondering, do you have results for the infamous 200129 with your method? Do we see
any significant movement in the spin posteriors?
So we didn't run on 2129. We chose to run on GW 191109. But we can definitely run and see what happens. Yeah, we just chose not to for that case.
I was also curious about this. Sorry. I was also curious about, which models are more accurate in which regions and parameter space. Is that, the difference of who the winner is in different places, is that kind of deliberate or is it accidental? And I guess whether or not the answer to that is yes, does that suggest a strategy where you might sort of start to look for particular models that could contribute to your method that work in particular regions of parameter space where we're starting to see, sort of significant source populations or something like that?
Yes, that's a good question. In my opinion, I think it's not accidental as to which models are more accurate in different regions of the parameter space, and it's to do with where each of those models are calibrated against. So, for instance, the model that that I worked on, we calibrated to a set of certain numerical relativity waveforms, and another model used a different set of numerical relativity waveforms. So you would argue that the model, when evaluated at those set of binary parameters, would be more accurate to numerical relativity than the other model. So I don't think it's an accident. I think it's just a case of which numerical relativity simulations you calibrate to when you do that. But that brings about a very important question I think you alluded to as well, which is it's much easier to generate a model that's very, very accurate to a very small region of the parameter space. It's much harder to do it over the broad region. So that's where something like this could also come in about. You make lots and lots of very accurate models over very small regions of the parameter space, and again, you sample over them as a result. And that, I think, could be a very interesting consequence as well. Yeah.
Thanks. For the procedure you just described, where you have lots of very accurate models, is there any downside to doing that? Where I don't know, maybe if you would want one model that sort of globally describes the data, is there some downside to having lots of models which are only accurate in very small regions?
It makes it a little bit more challenging if you were to. It's a lot easier to just say I'm going to use one model over the whole parameter space when you're sort of analyzing a population of candidates. So in that sense, it's a lot easier to say I'm just going to use one model that is fairly accurate over all the parameter space. But I think it's much better to do, for example, what you're describing, which is we take a very accurate model over very small regions of the parameter space and sample over them. I don't think there's a huge benefit to just using one model. Apart from it makes it easier to explain what's going on and which model you're using.